Okay, this is the third video of Module 4, a short one tying up some loose ends, starting with some specific nomenclature of alcohols and amines. So if you remember with carbons, and we're referring to, for example, this carbon right here is a primary carbon, and we show it like that because it's attached to only one other carbon. So primary, secondary, tertiary for carbons is defined based on how many carbons that carbon is attached to. So for this carbon, it's a secondary carbon attached to two other carbons. This is a tertiary carbon attached to 1, 2, 3 other carbons, tertiary. And then quaternary carbons are attached to 1, 2, 3, 4 other carbons. I have not seen it written like this, but maybe it is. You can check me on that. Usually we just call them quats for short. So amines follow a very similar pattern. So the amine nitrogen here, for example, is attached to one other carbon, so it's a primary amine. This is a secondary amine attached to two other carbons, a tertiary amine, and you can have a quaternary amine, but it will be charged, right, because of the nature of formal charges. Alcohols are a bit different. They're defined by the carbon they're attached to. So you're not looking at what's directly attached to the oxygen of the alcohol. You're looking at what's attached to the carbon that the oxygen of the alcohol is attached to. So here's our alcohol, oxygen. It's attached to a carbon that's attached to one other carbon. So that's a primary alcohol. This alcohol carbon is attached to two other carbons, so it's a secondary alcohol. The alcohol carbon here is attached to 3 other carbons, and so it's a tertiary alcohol. And you can't have a quaternary alcohol. Okay, so that's just how we refer to certain kinds of alcohols, amines, carbons. So if you look at the molecule morphine, for example, we have, well, to begin with, we have an ether. A little bit of review. Then, oops, I almost wrote ester. Isn't that tempting? Ether. We have what looks like an alcohol here, but when it's attached to an aromatic ring like this, we call it a phenol. However, here's an amine. Here's our amine. It's attached to 1, 2, 3 other carbons. So this is a tertiary amine. This alcohol here is attached to a carbon that is attached to 1, 2 other carbons. So this is a secondary alcohol. So morphine has an ether, a phenol, a secondary alcohol, and a tertiary amine. Now, tying up a few loose ends on carbonyl groups, carbonyl-containing functional groups. If you look at a ketone, remember it is polarized. It has inductive effects. If it's reacted with base, it will typically react in this way with the base forming a bond to the carbon and displacing this bond up toward the more electronegative oxygen. So you get to something like this as a first product. If it's reacted with acid instead, it's much more likely that the electrons of the lone pairs of the oxygen will be protonated by the acid, or more realistically, will pluck off a proton from an acid, since it would be acting like a Lewis base, and you would end up just protonating initially, at least, the oxygen of the ketone. So ketones' behavior is completely governed by its polarized nature of delta minus delta plus. Really, all of the carbonyl containing groups are dominated by that, but when you add another oxygen, say like in an ester, you have delta minus, delta plus, and another delta minus, and you have more things that can happen. So if we add a base, like we did above, it will likely be drawn toward, or attack, more likely is how we say it, the carbonyl carbon. Since it's delta positive, it will push these electrons up. So everything the same so far. And that will get you to this point here, which, if you notice, is reversible. So you can draw the arrows for the reverse reaction like this, and it gets you straight back to where you started. So I'll get rid of those for now. However, it can proceed, and this is probably what it does more normally, by these electrons coming down and displacing this group as a leaving group. Which, if you notice, gets you to a carboxylic acid. So that's kind of a unique, this part especially is unique to these carbonyl groups that have oxygens or other heteroatoms like nitrogen, sulfur, for example, maybe, in two positions attached to the carbon. So you could write exactly the same sequence with an amide, with an acid chloride, for example, throwing in new functional groups a little bit. Carboxylic acids are, and I will mention that in acid solution, if we were to react, say, this ester with an acid, you would probably expect protonation at the ester carbonyl oxygen, just like you did with the ketone. There's a lot more chemistry of these kinds of compounds, but this is just a brief initial survey. Carboxylic acids are unique because of the acidic proton on the end. So this will be removed in base, and probably in acid, either the carbonyl oxygen, either of the oxygens may be protonated in strong enough acid, or because carboxylic acid is itself an acid, if the acid isn't that strong, it would just be unchanged. I'll just add that, unchanged, however, in mild, or I almost wrote mild or moderate acid. I'll just leave it like that. Remember the bonding structure, of, say, a ketone or an ester, where the inductive effects are, where the electron density typically lies. So if you write, as I did in bottom, with the electron density in red, a ketone is much more polarized. It's just got the electronegative oxygen pulling electron density toward it, away from the carbon. But any of these kinds of arrangements, like an ester, amide, even a carboxylic acid, has a spread of electron density over all three atoms because it's sort of flowing back and forth around all three of these atoms. In fact, there's an older nomenclature where we would draw something like this to suggest that that negative electron density can be spread, or is, it's sort of more mobile, flowing across all three of these. So the upshot of that is that the carbonyl carbon of esters, amides, carboxylic acids, and so forth, are less delta positive than the ketone carbonyl group. And that influences the reactivity, like we saw above. So we're going to switch gears pretty soon here with Module 5, going into how we prove and determine the structures of organic molecules. Can't go too far without realizing that that's a necessity. And then we'll get back into structure and bonding with more stereochemistry, and then finally some more reactions at the very end. So all of this is seen again throughout the year-long organic sequence, actually.